The frictional force is actually related to the normal reaction. They are related to the normal reaction. And in the textbook, they have given, I think, four cases, right? Four cases on the normal reaction. The first case is this one. The first case is normal reaction on a level surface. The second one, normal reaction on a level surface, but there is an applied force. Okay, there's an applied force. The third one is normal reaction on the surface under acceleration. Now, how can a surface under acceleration? It means that what is the normal reaction when you are inside a lift? Okay, when you are inside a lift, what is the normal reaction of your feet against the floor of the lift, right? So actually there are six cases. Actually there are six cases. Another one after the case number three is case number four. Case number four is the object is resting on an inclined plane. So inclined plane, the normal reaction is not vertical, but is perpendicular to the inclined plane. So there are four cases that is stated inside the textbook. So we look at the first and the second case. Okay, the first case, normal reaction on a level surface. So this is a level surface. The table here is the level surface. This object has a mass of m, and there is a gravitational force of mg acting on the object, right? So the normal reaction means perpendicular to the surface of the table, there is a reaction. And that reaction, according to Newton's third law, is also equal to mg, but it is opposite of mg, right? So I enlarge the picture over here, right? They are very small, enlarge here. So the weight of the object exerted on the table, mg. The table exert a normal reaction on the object. And although we do not know the magnitude, how much is the normal reaction, but Newton's third law tell us, oh, it is equal to this mg, right? So N equals to mg, the normal reaction. Right? In our local textbook, they don't use N, they use R to represent the normal reaction. So this is the first case when the object is resting. However, we in practice, there are many variations. So the first variation is, let's say, for example, you apply a force on the object. Will the normal reaction will it still be equal to mg? So the example is like this. This girl, this girl or this boy, little girl, little boy, I don't know, is sitting on this sledge, and his father or her father is pulling, let's say him lah, pulling this boy along. Okay, the force exerted by the father is not parallel to the surface, but it is at an angle with the surface. So how much is the reaction of the surface on this boy? Or if you cannot imagine, you think that this woman is pulling a trolley. If you go to the supermarket with a trolley, if the trolley is resting, the woman is not there, then there will be only two forces acting on the trolley. One is the mg, the other one is the normal reaction, the N. However, if the woman is pulling the trolley upwards, so there will be an applied force. This applied force, I color it red in color. The woman is pulling the trolley, right? So the situation will be different. The normal reaction will be different. Now, in the second case, there is also an applied force. The man is pushing the boy. He's pushing downward a little bit. Not exactly vertically down, but at an angle, right? So this man is pushing the boy, and the normal reaction of this boy with the surface is different. Okay, it's no longer N equals to mg. So we're going to see what is the difference. So this case is similar to a woman pushing a trolley. So when the woman pushes a trolley, she's exerting a force downwards, not vertically downwards, but at an angle downwards. So when you're pushing like this, the reaction between the trolley and the surface provided by the surface of the floor, or the floor lah, the surface of the floor is no longer equals to mg. It will be different. So how much difference? We are going to analyze the force. By analyzing the force, we are going to resolve them into two components. Okay, so we look at the first case. In the first case here, the object is, at first it is resting. There will be the mass acting on the object, and there's a normal reaction. Now, if you are pulling this object with a force F, the red color, you are pulling the object, then the N here is no longer equal to mg. It's no longer equal to mg because you are pulling the object, you are exerting a force on the object, so the normal reaction will be different. But the weight of the object is still the same. It's still mg, right? So let's say the force is acting at an angle of theta. It's acting at an angle of theta with the floor. So I'm going to replace this red color force with two components. The two components, they are F sine theta, which is the vertical component, and F cos theta, which is the horizontal component. Okay, so when you resolve the red color force into the two blue colors, so the red color one no longer exists. I have exchanged my $1 note with two 50-cent coins. So now we look at these two 50-cent coins, right? Now these two 50-cent coin is actually my F sine theta and F cos theta lah. Okay, so comparing the vertical component of the forces, vertical component of the force. So how many vertical component are there? The normal reaction, F sine theta, and the mg. These are the three forces acting vertically. Now, when there are three forces acting vertically, your trolley is not jumping up and down. Your trolley is still moving horizontally. So the force, the vertical forces, they must balance one another. How they balance one another? The n and the F sine theta, n plus F sine theta, is equals to mg. The two forces acting upward is balanced by the force acting downward. So I say that n plus F sine theta equal to mg. So how much is the n now? The n is actually mg minus F sine theta. You bring this F sine theta over. So the normal reaction now is no longer mg, but is mg minus F sine theta. Mg minus F sine theta. Okay. Any questions so far?
No questions, sir.
No question. Now, just now we look at the vertical component of the forces. Now we look at the horizontal component. There's only one component there, F cos theta. There's no component going in the other way. But in actual practice, there will be frictional force, there will be frictional force along. So if this is the smooth floor, then the accelerating force will be the F sine theta. So net force will be, sorry, F cos theta. The net force will be F cos theta because there's no frictional force. But this is not the case. Later on, we are going to add the frictional force, right? So for the time being, if there's no frictional force, then the net force is F cos theta. Better put that if there's no frictional force. If no frictional force. Okay, if there's no frictional force, then it will be like this. Okay, now we look at the second case. The second case is pushing, not pulling but pushing. Now, pushing means the force is acting downwards. The red color force is acting downwards. So this red color force, I'm going to resolve it into two components. The two components, they are the horizontal component, F cos theta, and the vertical component, F sin theta. Okay, so when you resolve the red color into the two blue colors, so the red color no longer exists. So don't look at the red color anymore. Now, compare the vertical components. Compare the vertical components. The vertical component, they are N, mg, and F sin theta. N, mg, and F sin theta. Now, these forces, they are balancing one another. They balance one another. So how is it balanced? The upward force, N, equals to the downward force, mg, and F sin theta. So I say that N equals to mg plus F sin theta. So the force that is up balance the two downward force. So the normal reaction is more when you push. When you pull, the normal reaction is less, mg minus F sin theta. When you push, it is mg plus F sin theta. So that is the difference. The difference is in the normal reaction of the object or the normal reaction of the trolley. Okay, now we're going to look at the horizontal component. Horizontal component only one, F cos theta. And if there's no frictional force, then the accelerating force will be the F cos theta only, right? Will be F cos theta. So that is the difference between pulling and pushing an object, right? Pulling, less normal reaction. The normal reaction is less. Pushing, the normal reaction is more, right? Pulling is easier. When you pull the trolley, you use less effort. When you push the trolley, you are using more effort, more tiring. But if you push, it is easier to control the trolley. When you pull, you cannot see the trolley is behind you, so it's quite difficult to control. That's the difference. So if you have no question, then we stop here. Next lesson only we do this third and fourth case, right? Any question? No, no, then we stop here.
Okay. See you next week.
Okay,
Sir.
same time, 10:30. Bye.
Yes.